Okay, can start now? Okay. Hi, everyone. Thanks for being here today. My name is Nguyen Đăng Minh. I'm a machine learning engineer at Shopee. Today, I will present about LightSAGE, graph neural network for large-scale item retrieval at Shopee recommendation advertisement. So the author is me, Chen Fei, Shen Yan, and Ethan. This is the outline the sharing. So first, we'll present about the problem of recommendation problem at Shopee, the challenges and our solutions when applying GNN to solve the problem, and lastly is the evaluation result. So first, a brief introduction about Shopee. So if you are interested in the stock market, you may have heard about us. In the last 4 years, our stock price increased 10 times and then dropped 10 times. But not only about stock price, we are also known as a major e-commerce platform in multiple markets in Southeast Asia and Latin America, with tens millions of sellers, 100 millions of buyers, and billions of listing products. So this is to show that at this scale, any improvement in the recommendation quality will have a huge impact on many people as well as the revenue of the platform. So here we are trying to solve a classic recommendation problem. Given that the user is viewing an item, we will try to recommend him with products relevant to his viewing item. So it is an item-to-item recommendations. The framework to solve a recommendation have several stages: retrieval, ranking, and ranking. Here we focus on the retrieval stage. So the problem is retrieve items that are relevant to a given context from a pool of billions as items. One of the popular solutions for this problem is vector search on items embedding. That means we try to represent each item with an embedding, and finding a relevant item is the same as finding two similar embeddings. So the critical part to the success of this solution is the quality of the embedding. And one of the best methods to produce the item embedding is via graph neural network. Why graph neural network has the advantage is that graph neural network is the deep neural network applying on a graph. So first, it has a large learning capacity. Second, thanks to the graph, it can capture rich user item features and their interactions, making these solutions more advantageous as compared to classical collaborative filtering or conventional deep neural network. So our direction is to build, because since it is an item-to-item graph, so we will build a homogeneous item graph with item as the only node types, and then we will train a GNN on the item graph to obtain items embedding and perform vector search on item embedding for retrieval. In order to, on the path to implementing these solutions, we encounter three main challenges. First, graph construction. Second, model architecture. And last, long tail and constant handling. I will detail each of these challenges and the solution one by one. The first problem is graph construction. So garbage in, garbage out. If your graph is bad, then no matter how good your model architecture is, as the result, the final result will be bad. Most of the existing work construct the graph from user click sequence. That means if your click sequence is A, B, C, D, then you will form a link between A, B, B to C, then C to A. However, for e-commerce, then this kind of logic will result in a very noisy edges. This is an example of an actual user click sequence in Shopee. You can see that the user interest shift very quickly from male fashion to dental care to mobile accessory. So if you follow the conventional way of building the graph, you will end up with a very noisy graph. Our solution is we construct a graph from only high confidence click. What is high confidence click? That is, you are click in only a very specific scenario. You are viewing a product viewing a product B, then click product A. Then we will link B to A. So only if you click in this scenario, then we will form the link. That is what it means to be high confidence click. But if you only consider this type of click, then your graph will be very sparse. and have low item coverage. So in order to make up for this, we add artificial link from CF algorithm. Here that means if the algorithm say item C should recommend item A, then a link is formed from C to A. Here we use two CF algorithm, which is swing and co-search. So as a result, we have an item-to-item graph that is both high precision and high density. There's only one node type, which is item. The edge can be based from actual click or artificial link by CF algorithm. That is the problem with the graph. Now comes the problem with the model architecture. The challenge is there has been a lot of research on GNN architecture, but not all of them are applicable in in real life scenario and is scalable. The two most popular model is LightSAGE and PinSAGE. LightSAGE is well known for its efficient aggregation logic. However, it is not realistic to apply at real life because it considers all neighbors. Meanwhile, in real life, one node can have thousands of neighbors. PinSAGE is scalable and can be applied at real life because it has the neighbor sampling method, but the aggregation logic have room for improvement. So our solution is very straightforward. We combine the best of these two, meaning we combine neighbor aggregation of PinSAGE we combine aggregation logic of LightSAGE with neighbor sampling of PinSAGE, which result in the name LightSAGE. For the details, then first we do neighbor sampling to reduce computational cost similar to PinSAGE. Then we have the neighbor embedding aggregation logic just like LightSAGE, and this is the training pipeline. So one data sample will have a target node, a positive node, and a negative nodes. The task of the GNN is that it must produce the embedding such that the embedding of the target node need to be as similar as the positive node as possible and as far away as the negative node as possible. So the training task is multi-class classifications using categorical cross entropy loss. So this is the second problem, which is in the model architecture. The third problem is long tail handling. So we encounter two kinds of troublesome items. First is the item that have low click, because 5% of items account for 95% of user clicks. That means you have a huge amount of items with no user click whatsoever. Second is cold start. That means every day there are new items with new user behavior appear. The problem is even more severe in ads, because that's why people use ads, right? They pay money so that their new item or their low click item can have a better chance. So for this item, they don't have user click. They do not appear in the graph. So there is no way for the GNN model to produce the embedding. So the challenge is how to produce the embedding for no click and new items. Our solution is that we use the GNN to produce the embedding for the hot item or the so-called seed items. Then we use the hot embedding to map to produce the embedding for the cold item using two kinds of strategy. The first strategy is that for items that is new, it doesn't have click now, but it may have click tomorrow or next week. So the moment it have click, we can link them with existing hot items. Then for a cold item that have a hot neighbors, we can average the embedding of the hot neighbor to form the embedding of the cold item. That is the first strategy. The second strategy is for item with no click whatsoever. Then for this type item, we rely on its contents, such as attribute, category, brands. We find the hot item that have the similar information with the cold item and average the embedding, and that will become the embedding of the cold item. So using these two strategies, we can cover embedding for 100% of items, and we can update our embedding with the latest item pool and latest user behavior. So this is the offline evaluation result. The baseline is the node-to-vec on the traditional graph view using click sequence without tail handling technique. So here we have details ablation study where we incrementally add the improvement in terms of model, graph, and tail handling. As the result, the final model, which contain all of the improvement, see a recall rate increased by 88%, and the tail recall rate increased by 300%. Not only achieving a good offline performance, our work also achieved a good performance when deploying online. We see the ads order increased by 1% and ads revenue increased by 5%. Not only improving the business metrics, we also improve the healthiness of the platform ecosystem. As more items have the chance to have impression and clicks. So as the result, the model is deployed online. So if you open the Shopee apps, you scroll down, you enter any product page, scroll down to the You Miles Online section, then that's where you find the result of our model. So in conclusion, I have presented the product recommendation problem at Shopee, which is retrieve item relevant to our target items. The direction is vector recall with GNN. There are three main challenges when implementing this solution. First is graph construction, second, model architecture, third is long tail and cold start handling. For each challenge, we have details our solutions. As a result, we achieve a good offline performance in terms of long tail and unique hit rate. And for online, it has improved business output and platform healthiness. So yeah, thanks a lot for your attention.
All right, thank you. Questions? I did not see any on Slido. So I do have a question. You are getting your edges from both real, user interactions and then also from these recommendation algorithms. Are those different edges treated differently in the model, or are they treated just exactly the same?
Okay, so the edges are treated, initially they are treated differently. So we assign weights for each kind of edges. So the real click, of course, we have a higher weight. The artificial click, we have a lower weight, depending on how confident the algorithm are. Then in the end, they will be converted all to the same space. So there's only one edge type, but the weight will be different.
Is it working? Okay. Hi, thank you for the presentation. It was very interesting. I have a question regarding the negative sampling. I saw that you use a random negative sample and an hard negative sample, and I was wondering if there's a specific reason and why, how it is differ from a curriculum training negative sampling, where at the start you sample a random negative, and as the training proceeds, you sample harder and harder sample.
Oh, yeah, okay. So, yeah, thanks for your question. That's exactly what we did, is that we, at the beginning, at the first epoch, we only have a random negative. So as the training go on, we started adding hard negative. So after, I think, 3 epochs, then we will have both random negative and hard negative. That's exactly what we did.
Okay, thank you so much.
There's a question? Okay, I can get it here. I got my phone. All right, looks like we have an online question. Here we go. Okay, so the question is,
yes,
is the model sensitive to any particular type of user? For example, people who click a lot without buying anything.
I see. So, okay. So in terms of sensitive to certain type of user, there can be many type of user. So we have some filter to filter our spam user. That user that have abnormally amount of click, then we will have some logic to filter them out. But for the specific user that is being asked, then the answer is no. Because as you can see, the model is trained on task, on click. So it's trying to maximize the click probability. It doesn't consider purchase information. So for that type of user, then no, the model will not be able to handle them.
Okay. How are we doing on time? Okay. All right. So I get to ask my last question. So So the cold start issue, you sort of talked about how to address that by finding, kind of similar items. But it struck me that you could take the same logic you had in terms of, using a recommender system to increase the density of the graph. You could take a content-based recommender and use it to recommend from the cold item to the items that are already in the catalog and add edges to the cold item in that way. I was wondering if you thought about that as a way to handle the purely cold items.
Yes, thanks for your questions. So let me repeat. Your question is, I could have used a content-based link, which can make the graph richer and also contain the cold start item in the graph during training.
Right.
Yes. Okay. So yes, we have considered that, but we did not do it. First reason is we want to. First one is the resource constraint, because if we include all item in the graph, our graph is huge. In the scale of billions of items, then we cannot handle the computation. So that's why we do not consider adding all item in the graph. Second is when building the graph, our priority is the graph need to have very high precision. So the goal is to build the best embedding possible. We do not put embedding coverage as a priority at the training stage.
Okay.
So that's why we only consider collaborative filtering, which have a higher precision as the content base. But during the inference stage, when we in the first strategy, when we as you can see, this is just a link between the cold and the hot item, right? Then when we build this link in the inference stage, then we do consider content-based link as well.
Yeah. All right. Thank you. Let's thank the speaker.
Yeah. Thank you.